Okay, so we're going to start up with our final exam review. So the style of the review is as follows. I'm going to pose test style questions for everyone, and then I will give you a few minutes to answer individually, and you'll submit your answers to me privately. So you'll just direct message me on Zoom, and that way I can see what answers people are giving. And then if a question is answered correctly by almost everyone, then I'll give a quick explanation. We can move on quickly to the next question and get more practice. If there's some disagreement, so here now, if there's some disagreement, we'll discuss the question in teams. So I'll put you guys in to the rooms, maybe just one room based on how many people we have right now, but hopefully more show up. And then you can just discuss the answer, try to convince each other that your answer is correct, focusing on the logic there, the reasoning, and see if you can convince your partners to change their answer. And then last, if almost everyone answers incorrectly, then what we'll do is I will give the explanation. So if almost everyone answers incorrectly, I will explain everything related to that question. So I'll just end it there. So I'll explain everything, and we'll see where we stand on that, answer any questions if there's any questions about that. Okay, so the chapters that we're covering here, just briefly, we're going from chapter 2 all the way up to chapter 13. And so what we'll do to start is to try and do maybe 2 questions from each chapter. And the questions will be all exam style. And we'll just see where we are from there as far as the time. And then we'll just, whatever people want to, okay, we want to see another question from chapter 6, I can just pull up another question. I have tons of questions. I'll just be using a test bank to kind of rapid fire these questions off. And you guys know that sometimes I'll put an exact copy of a question on a test that you've seen before. And then, of course, there's a lot of like newer questions you haven't seen before. So, and in some cases, I may take an exact question, but maybe change a number or something, or change the wording. So there you go. That's what we're doing today. Before we jump in to the actual question asking part, there's one other thing. I created a final exam review assignment, and it is posted on Mastering Physics. It will become available as soon as we hit 10 o'clock tonight. So after this roughly 3-hour session is over, that assignment will be available. It's 2 questions from every chapter, 1 conceptual question, 1 calculation question. So it's not going to cover every topic that you should study, but at least it'll get you started and get you thinking about those the topics basically in those chapters. Okay, so let's go ahead and get started with the first question now. So we'll begin just from the beginning. So chapter 2. Okay, so I'm going to go ahead and now type out a question here. Don't want to copy paste because then the font is not the right size. So we want to make sure we can see everything clearly here. You can be thinking about the question while I'm kind of writing it out. But I'll go ahead and read it before we get started here. Okay, so I'm done typing. So let me just read the question once, and I'll read the answers once, and then I'm going to pause the recording. If you're watching on YouTube, you can pause the video, because once I pause the recording, right, we're just going to skip over the discussion time. So you'll want to pause the video and think about the answer and commit to an answer, and then I'll reveal the answer when we come back. Okay, so which of the following quantities has units of a displacement? There could be more than one correct choice. So this shouldn't be a difficult question. This is like a real warm-up question. 32 feet per second squared, 40 kilometers southwest, minus 120 meters per second, 9.8 meters per second squared, or 186,000 miles. Okay, so if you're watching the recording, again, just pause the video and we'll be back with the answer shortly. All right, so we're back and hopefully you had time to think about that and you came up with B as the correct answer because B has direction, right? So um, B is a displacement, okay? Another candidate here for the answer would be answer E, but notice that this one has no direction. All right, so let's go to the next question. Okay, so we're back with the next question. So here it is. A ball is thrown straight up, reaches a maximum height, then falls to its initial height. Which of the following statements about the direction of the velocity and acceleration of the ball as it is going up is correct? So A, both its velocity and its acceleration point upward. B, its velocity points upward and its acceleration points downward. C, its velocity points downward and its acceleration points upward. And D, both its velocity and its acceleration points downward. So go ahead and pause the video if you're watching the recording. Give this one a shot by yourself. We'll be back in an instant to discuss the answer. Okay, so we had some good discussion there. We came finally upon the answer after some disagreement that the answer is B. The velocity points upward and the acceleration points downward. So this is a classic example of a projectile motion style problem where we have a ball being thrown upward. So its velocity is pointing upward as it moves up, but there is gravitational acceleration downward, right? And that gravitational acceleration never changes directions. It's always pointing downward. And the velocity is going to point upward as the ball moves up. It's going to be zero at the highest point, and then it's going to point down when the ball begins to move down, right? So for this particular question, it's asking what the velocity and acceleration of the ball are as it's going up. So we get its velocity points upward and its acceleration points downward. All right, we'll be back with the next question in just a moment. Okay, so we have the first question out of chapter 3 now. Two displacement vectors have magnitudes of 5.0 meters and 7.0 meters respectively. If these two vectors are added together, the magnitude of the sum is equal to 2 meters, could be as small as 2 meters or as large as 12 meters, is equal to 12 meters, or is equal to 8.6 meters. So if you're watching the recording, again, pause the video, give this one a shot by yourself. Those of you who are here now, I'll give you some time to think about that and commit to an answer. And then I'll let you discuss if there's some disagreement. So I'll see you back in the video in just a moment. Okay, so we're back and we had some agreement here on the answer for answer B here. This is the correct answer. Of course, we can have vectors in the following way, 5 meters in this direction and 7 meters in this direction, right? And so the vector sum of these will be less than 12 meters, and it will be more than 2 meters. How could we get 12 meters? We could put the vectors like this, 5 and 7, right? And then that would give us a resultant vector, which is 12. Or we could flip the direction on the 5 meters, have something like this, in which case our resultant vector here would be 2 meters. So let's go ahead and fill that in real quick. So 2 meters, this one would be 12. And this one, this resultant vector here would have a magnitude less than 12 meters. but it would also be greater than 2 meters as well. So there you go. So when you add vectors like that, you have to be careful. You have to remember that vectors not only have magnitudes, but they also have directions. Okay, so I'll see you for the next question. Okay, so we are here with the next question. Now we're going to start mixing in some calculation questions into the review. So a ball thrown horizontally from a point 24 meters above the ground strikes the ground after traveling horizontally a distance of 18 meters. With what speed was it thrown, assuming negligible air resistance? Now, since I've already informed everyone that I will be giving formulas on the final exam, let's go ahead and write down maybe some relevant formulas here for this question. So I'll actually open this up to those who are here. So does anyone want to give some input as to what might be some useful formulas here? So these would be kinematics equations. Anybody have any ideas, or we're stumped? Okay, maybe let me help. Maybe something like
Maybe
this.
Yeah, I was gonna say like some linear motion equation.
Okay, so yeah, x final equals x initial plus what comes next? Initial velocity, right?
Initial time.
Time, no, the time that it's traveling with that velocity, not the initial time.
Yes.
Really, if we want to be really accurate here, this t should be a delta t, but it usually gets really tedious to keep writing delta t over and over. And then plus one half
acceleration,
and then
t squared.
T squared, right? So there's one equation that might be useful for us. Maybe in addition to that, we could also subscript that maybe this initial velocity is in the x direction, right?
Yeah.
And this acceleration here would be the acceleration in the x direction. And then in addition to this equation, we would also have the final y position. So you go to the final or the initial y position plus v initial y times t plus 1/2 a y t squared. But whenever we have projectile motion, right, this term right here always becomes minus g, right?
Yeah.
Okay. Any other equations that might be useful for us here? Or are you guys ready to start working on it? I'm just going to go ahead and give you guys some time to work on it, and I'll see everyone in the recording. Go ahead and pause at this point. If you need to look up some formulas in the book or something like that, go ahead. Like I said, I will give you a decent number of formulas on the final, so should be okay. See you guys in a moment. Okay, so we had a little bit of a discussion here. We're not quite ready to give the answer yet, but we've determined that because we're dealing with projectile motion, which involves vectors, we can break this thing down into x and y components, and we determined that there was no acceleration in the x direction. And so this top equation here reduces to a nice simple equation. X equals velocity in the x direction times t. And in fact, the velocity in the x direction does not change, so we don't even need this initial subscript here. Okay, so we'll be back in a moment with the answer. Okay, so this one took a little bit longer than expected, so I'll give a slightly more detailed explanation here. The correct answer for this one is C. And the way you figure that out is you start with motion in the y direction. So the y direction tells you how long this thing's going to be in the air, right? Because it's going to be in the air until it hits the ground. So in that case, you can write delta y equals minus 1/2 gt squared, where Here's our initial y position up there at 24 meters, and this is our final y position down here. So delta y is going to be minus 24 meters. G, of course, this is always going to be 9.8 meters per second squared. So we have the minus sign in the equation there to indicate the direction is downward for the acceleration. So we can solve this thing for t, and you go ahead and go through the algebra yourself. T is going to be the square root of 48 over 9.8 right there. Plug that into the calculator to get a value for t. That'll have units of seconds. And then what you want to do is you want to take this t here and use it to solve for the initial velocity in the x direction. There is only an initial velocity in the x direction because the ball is thrown horizontally, right? Okay, so how do we do that second part? Well, in order to solve for velocity, we can say that the velocity is the distance traveled in the x direction, so maybe we could put delta x over the time it takes to travel that distance. So since the ball is in the air for square root 48 over 9.8 seconds, we would calculate the velocity as delta x, which is given to us as 18 meters. And we would divide that by this number that we had before, so 48 or 9.8. Of course, you're working this on your calculator. You'll have a number here for this, right? Roughly square root of 4.8 if you want to take g to be 10. You can always do that on a test. Always a nice little tip for you when you're working through a test. Maybe always go through the question first, assuming g is 10 meters per second squared, just to make your calculations a little bit easier, a little bit more manageable. And then, you know, if you get an answer that is really close to one of the answers choices and all the other answer choices are much different, then you can just stop right there, right? And you can just pick that answer because 9.8 is only a little bit different from 10. But if you happen to get an answer where maybe there's two answers which are close, then you've ruled out the other two or three answers, right? And so then you can go in there and go back through your calculator and replace the 10 with a 9.8 to get the correct answer. Okay, so there's some little tricks there. What you get for this, of course, is 8.1 meters per second. So try that out yourself and make sure you can get that answer. All right, I'll be pausing the recording, get the next question up, and we'll be back here in just a moment. Okay, so we're back with the next question. We're now starting chapter 4. Actually, I forgot to write that up here at the top. Let's go ahead and write that. So we're on chapter 4 now. Chapter 4 is all about Newton's laws, right? Forces and things like that. So here's the question. A crate is sliding down an inclined ramp at a constant speed of 0.55 meters per second. The vector sum of all the forces acting on this crate must point, and then we have some choices, down the ramp, up the ramp, perpendicular to the ramp, vertically downward, or none of the above choices is correct. Okay, so if you're watching the video, again, pause, think about this one yourself, and we'll be back in a moment's notice with the answer and some discussion. Okay, so we're back. We seem to have agreement on answer A here, but answer A is incorrect. Let's understand why answer A is incorrect. In the statement of the problem, it says that we have a crate that's sliding down an inclined ramp at a constant speed of 0.55 meters per second. If the ramp is sliding down an incline with a constant speed, then that means it has constant velocity. So something like this, right, where v is constant. And therefore, the sum of all of the forces on this crate has to be equal to 0. And some of you probably recognize that if the sum of all the forces is 0, then there is no direction for the force vector. And so the correct answer here is E. And so I'll be back with the next question for those of you who are watching on YouTube in just a moment. Okay, so we're back with the next question, still in chapter 4 here. If I weigh 741 newtons on Earth at a place where G is 9.80 meters per second squared, and 5,320 newtons on the surface of another planet, what is the acceleration due to gravity on that planet? So first choice, 70.4 meters per second squared, 51.4 meters per second squared, 61.2 meters per second squared, and 81 meters per second squared. So pause the video now and think about this question. And we'll be back shortly with the answer and explanation. So we had a quick little discussion on what formula might be relevant here, since of course I'm going to give you some formulas on the final. So we discussed it briefly, and F equals ma seems to be a useful formula for tackling this question. That'd definitely be a formula that I would give to you. So hopefully that helps. We'll be back again with the explanation of the answer shortly. Okay, so we have agreement here on the answer for answer A. Answer A is the correct answer. So the way we tackle this problem is we first need to figure out the mass. So what is the mass? Well, the mass is the weight divided by the gravitational acceleration. Weight is a force, right? So once we find the mass on Earth, of course, the mass is the same everywhere in the universe, right? The mass is how much stuff makes up an object. So that's going to be the same no matter where you are. But the weight and the gravitational acceleration can change. So once we find the mass, then we can use the equation G equals weight over the mass to find the new value of G. So maybe we can call this G prime or something, just to give it another label. And I'll let you at home work through the math on that one. You should come up with 70.4 meters per second squared. All right, we'll be back again with the next question shortly, beginning chapter 5. Okay, we're back, and we have our first question here for chapter 5. So chapter 5 was all about kind of applying Newton's laws. Talked about things like cars on turning on the road or on banked roads, things like that. So when a car goes around a banked circular curve at the proper speed for the banking angle, there's a little bit of a typo there. So maybe let's fix that real quick. So when a car goes around a banked circular curve at the proper speed for the banking angle, what force causes it to follow the circular path? There's another typo there. Causes it to follow the circular path. Okay, our choices are the normal force from the road, the friction force from the road, gravity, or no forces cause the car to do this because the car is traveling at constant speed and therefore has no acceleration. Okay, so take a minute, pause the video if you're watching the recording, and think about this one, and we'll be back shortly with our answer and explanation. All right, we're back. We had a lengthy discussion there. It was pretty good. When a car goes around a banked circular curve at the proper speed for the banking angle, what force causes it to follow the circular path? The discussion was between two answers here, answer A and answer B. But in the end, we all agreed that it was the correct answer, answer A here, the normal force from the road. Just a quick review of banked roads. So a banked road represents some kind of inclined plane like this. So we just draw this triangle here, and we have our car. The back view of the car looks something like this, right? And so this car is going into the page, and eventually it will come around on some circular path here. Think the turn in like a NASCAR, on a NASCAR roundabout. So what force is making this thing go around in that circle? Well, there's only one force that has a component in the direction which is towards the center of the circle in this case, when it's moving at that proper speed for the banking angle. Okay? When it's moving at exactly that speed, only the normal force is in that direction. So the normal force looks something like this. Gravity is down like this. And so the centripetal force is exactly equal to this component of the normal force right here. And the horizontal component of the normal force. And the vertical component of the normal force perfectly cancels gravity. Okay. If the car was traveling a little bit faster or a little bit slower, then we would have to account for a friction force as well. But in this particular problem, the normal force is the answer. Okay, any questions from you two? I'm going to pause the recording. I'll have the next question up in a minute. All right, we're back. We have the next question here from chapter 5. A spherically symmetric planet has 4 times the Earth's mass and twice its radius. If a jar of peanut butter weighs 12 newtons on the surface of the Earth, how much would it weigh on the surface of this planet? So first, let's discuss maybe some relevant formulas here, right? Can anybody think of some formulas that are relevant for this question? If not, I can give some.
I think it's called Kepler's law.
Kepler's laws. Kepler's laws will not apply to this question in particular. Kepler's laws apply for orbits around planets, or like an orbit around a star or something. So not Kepler's law, but we're really close. His name starts with an N.
Is it Newton?
Newton, right? Newton. So Newton's law of what?
I didn't write. I just wrote
Gravity.
Newton.
Gravity. Newton's law of gravity, right? So do we remember what Newton's law of gravity is? I'll give you a second to see if you remember. So it's big G. That's the universal gravitational constant.
Mhm.
Is there some masses in there?
Mass of Earth.
Mass of the Earth is going to be in there. Let's put M1. Is there a second mass in there?
M2.
M2, okay. So there's 2 masses. And then what goes on the bottom?
The diameter squared or the radius?
Yeah,
squared?
so the distance between the two, right?
Oh, distance. Okay.
Yeah. You can think of it as an R or a D. It's really the distance between the 2 objects.
Okay.
So so this is Newton's law of gravity, right? And this is kind of what this question, you need to know some information about in order to answer this question. So we're being told that we've found a spherically symmetric planet which has 4 times the Earth's mass and twice its radius. Okay, so think about how you can evaluate what the weight on the surface of this new planet would be for this peanut butter jar. Okay, so I'm going to pause the recording. Those of you watching the recording, remember, pause the video, give this one a shot yourself. We'll be back here in just a moment. Okay, we're back. We had some good discussion there. We had some disagreement, and then we all came to agreement on this answer here, 12 newtons. I'm going to keep you in suspense here for a second on as to what the correct answer is. To do this question, we don't necessarily need to know the exact formula for the force of gravity. which would be equal to the weight of the peanut butter jar on the planets. We simply need to know that the force is proportional to the mass product, so m1 times m2, and is inversely proportional to 1 over the radius of the planet squared. So we could combine these and forget about the constant factor of g there. And furthermore, we could even forget about one of the masses, because one of them is the mass of the peanut butter, which doesn't change. So let's go ahead and X out mass 2 as well. In the question, it says that this new planet here has 4 times the Earth's mass. So what I'll do is I will write down force of Earth proportional to mass of Earth times, or divided by radius of Earth squared. And then we'll take a look at some second planet here. Maybe we'll call this force on the planet that has 4 times Earth's mass there, so 4e, proportional to 4me over twice, it says here that it has twice the radius of Earth, so 2 times r sub e quantity squared here. And we can see that the square of 2re becomes 4re squared, so we have a 4me over 4re squared, and the 4's cancel here. And so what we end up with is a statement that the forces on both of these, or sorry, the force on these, on this peanut butter jar is the same on both of these planets. Okay, the constant of proportionality here is just big G, right? It's not going to change the ratio of these two forces. So that means that the answer is 12 newtons. And so the force is the same. Okay, so I'll be back with the next question here. We still got another hour to go. I think we can get through a couple more chapters here. Okay, so we're back. We have our first question out of chapter 6, which is all about work and energy. So here is the question. I'll read it, and then we'll go ahead and pause. 2 men, Joel and Jerry, push against a car that has stalled, trying unsuccessfully to get it moving. Jerry stops after 10 minutes, while Joel is able to push for 5 minutes longer. Compare the work they do on the car. So we have 5 options here. Joel does 75% more work than Jerry. Joel does 50% more work than Jerry. Jerry does 50% more work than Joel. Joel does 25% more work than Jerry, and neither of them does any work. Okay, so we'll go ahead and pause. I'll give you some time to work on that. If you're watching the recording, we'll be back in just a second, so make sure you try the question yourself, pause the video. All right, so we're back, and we had agreement here on our answer. So the answer that was chosen was answer E, that neither of them does any work. This is the correct answer since the car does not move. So the velocity of the car is 0, so there's no displacement, right? So work is force that is done over a displacement delta x. So the product of the force times the displacement. Since the displacement is 0, the work is always going to be 0. It doesn't matter that Joel pushed for 5 minutes longer. Okay, so we'll go to the next question. I'm going to go ahead and pause and get the next one ready. We'll be back in just a second. Okay, here we are with the next question. What is the minimum energy needed to change the speed of a 1,600 kilogram sport utility vehicle from 15 meters per second to 40 meters per second? So 5 options: 1.1 megajoules, 10 kilojoules, 20 kilojoules, 40 kilojoules, or 0.96 megajoules. To remind you before I let you work on it, kilojoule is 10 to the third, right? Joules. I will not provide you with prefixes on the final, because then it'll just take up too much space on the formula sheet. So it is a good idea probably to remember these. 1 megajoule is 10 to the 6 joules. Okay, so those are the units there for our options. And finally, I'll open the floor up to the three of you who are here. What formulas are going to be relevant for this question in particular? So can we think of any formulas we can write down? Can we think of any formulas at all that will help us tackle this question here? We're given mass, we're given velocity.
The work formula?
The work, okay, so the work formula that we kind of used in our explanation last time. Okay, so work is force times displacement. Okay,
And
anything else?
the work is the change in kinetic energy.
Work is the change in kinetic energy. That's the work energy theorem, right?
Mhm.
So maybe what we should do is we should actually drop this part, right? Since we don't need, there's no force or displacement in this problem, right? So we probably need this one. What about the actual kinetic energy itself? Can we remember what kinetic energy is?
It's the mass times, I almost said volume, mass times velocity squared.
So mass times velocity squared.
1/2.
1/2, right?
Yeah.
So 1/2 mv squared. Okay, I think that's good enough to tackle this one. So I'm gonna go ahead and pause the recording now. So those of you watching the recording, pause the video, try this one yourself. Okay, we're back. So after some discussion, we are now in agreement that answer A here is the correct answer. And the way we show that that is the correct answer is with the work energy theorem. So kinetic energy final minus kinetic energy initial. So 1/2 mv final squared minus 1/2 mv initial squared. And I will leave it to the viewer at home to plug in the numbers and check that the answer that we get from this is about 1.10 megajoules after rounding. Okay, let's go ahead and try that yourselves. We'll go to the next question now. And I believe we are now headed into chapter 7, which is linear momentum. So I'll be back with the next question. All right, we're back with the next question. In the figure showing an isolated system, determine the character of the collision. Meaning, is it inelastic? Is it elastic? Maybe it's super elastic, which would mean that somehow energy was added. There's like an explosion or something. Okay, the masses of the blocks and the velocities before and after are shown. The collision is, and this is the schematic here for the collision. So we have a 9 kilogram block moving to the right with 2.1 meters per second. We have a 3 kilogram block moving to the left with 0.6 meters per second. So that is the state of the two masses before the collision. And then after they collide, both blocks are moving to the right with the same velocity, 1.5 meters per second. Right? So the answers that we have to choose from is that it is a perfectly elastic collision, a partially inelastic collision, a completely inelastic collision, characterized by an increase in kinetic energy. That's a super elastic collision. And finally, not possible because momentum is not conserved. Okay, so if you're watching the recording, pause the video here, give this one a shot yourself. we'll be back in just a moment to discuss. Okay, so after some discussion here, the group came to the answer C, that it was a completely inelastic collision. A completely inelastic collision is characterized when two objects stick together. So when the objects stick together, that's completely inelastic. And you can see that that is the case here. Although the diagram shows a little bit of a gap between the two blocks, the diagram is really just telling you their masses and their velocities. So if the two objects collide and have exactly the same velocity, then of course they have to stick together. There's no other way for that to happen. So this one is correct. Answer C, a completely inelastic collision. Okay, that was our first question from chapter 7, which I forgot to write it up here, but I do remember saying it. So we'll go to the next question in just a moment here. All right, so we're on to the next question now. A 0.14 kilogram baseball is dropped from rest from a height of 2 meters above the ground. What is the magnitude of its momentum just before it hits the ground if we neglect air resistance? So 0.28 kilogram meter per second, 0.88 kilograms meters per second, 0.44 kilogram meters per second, 0.62 kilogram meter per second, 1.4 kilogram meter per second. Now this question is drawing on knowledge from not just chapter 7, but you also need to know a little bit about chapter 2 and 3, right? So some kinematics. So you'll need to figure out some things here. So I'll open it up to those of you who are here. Can you think of any formulas that might be useful in tackling this problem?
Momentum is the mass times velocity.
Okay, momentum, which we use P for, right, is mass times velocity. So I'm reading the question again. I don't see any mention of velocity, but I see a mention of a height. Is there a way we can find the velocity given that this object is dropped from a certain height? Excuse me.
Is that gravity times height?
Gravity times height. You're headed in the direction of potential energy, I think.
Okay.
Well, let me go ahead and give you an equation which might show up on a formula sheet. And that would be that if we were to drop a ball from a height h, then the time that it takes to fall that height h, we could find from this equation here, where I've canceled a minus sign on each side of the equation, so I could just work with positive numbers here. And then once we find the time, we could maybe use another formula to find the velocity. This formula right here, which is the velocity equals the acceleration times the time. So maybe with those two extra formulas, which might show up on a formula sheet, then we would be good to go for this problem. Okay, so that's where I'll pause the recording. So if you're working on this by yourself at home, pause the video now and try to work this one out, and we'll be back in just a second. Okay, we're back, and we had some nice agreement here on the answer B. Okay, so let's take a look here. From these two equations right here, we can get an equation for the velocity when it hits the ground. And in order to do that, maybe I can just make a note quickly over here on the side. We want to solve for t. So t is 2h over g in a square root. And if we plug that into this expression here, we get g times square root of 2h over g. And the square root and the g cancel. You can think of g as square root of g, quantity squared, and you can bring it inside the square root. What you end up with is square root of 2gh. So the velocity is square root of 2gh. That's something we can calculate from what we're given, right? We just use 9.8 meters per second squared for g. And then we can multiply by the mass to get the momentum. So all said and done, throwing it all together, we'd have that the momentum is 0.14 for the mass. I'll leave the units off, but make sure you understand how the units work out here. 2 times 9.8, this is under the square root here. And then for the height, 2 meters. Okay. And so this is approximately going to come out to, let me just plug it into the calculator here, since I didn't check it myself. And we do indeed end up with 0.876, which will round up to that 0.88 kilogram meter per seconds there for the unit. Okay, any questions on that one? I'll see you guys here in a second for the next question. Okay, so for this question, we're beginning chapter 8, which was things like rotational motion, rotational dynamics, and kinematics, and torque, angular momentum, those kind of concepts involving rotation and rotational inertia. So here we have a question with a nice figure. As shown in the figure, a given force is applied to a rod in several different ways. In which case is the torque about the pivot P due to this force the greatest? Okay, so the pivot point P in all of the diagrams here is on the left end side of the rod. And then the force F is the same magnitude, but is being applied at different locations on the rod and in different directions. So the choices here are 1, 2, 3, 4, and 5. So each of those figures individually has a number. So that's how you'll choose your answer. Okay, so if you're watching on YouTube, just go ahead and pause it, give it a shot yourself, and we'll be back in a second. Okay, so after some discussion here, we've settled to the answer corresponding to this figure here, which would be answer A. So the important thing to understand here is that torque is force times lever arm, right? So force times lever arm. And the bigger the lever arm, which is the distance from the pivot point to where the force is being applied, and the force that causes the torque has to have a component which is perpendicular to that lever arm. So we either put the symbol here F perpendicular, or we say the torque is FL sine theta, where theta is the, for example here, this one is making an angle. Theta is the angle between the lever arm and the force. In that case, it's this angle up here at the top because the lever arm is pointing in this direction. So you could imagine that this force right here is pointing in this direction. And so it's really this angle theta that's important here. For this one, it's a little bit tougher to see because the angle is it's almost 90, but it's not quite 90. This would be the angle theta right here. Theta is almost 90, which means it's almost 1, right? Sine of 90 is 1. In this case right here, we have a 90-degree angle. So the sine of theta is 1. But sine is always less than 1 if the angle is not a multiple, is not 90 or plus 180, which would be 270. And so it's slightly less torque. Option 3 is slightly less torque than option 1. So the torque for 1 is bigger than the torque for 3. Okay. Which one would be the next biggest torque? It depends, actually. 2 and 4 could have the same torque if the angle theta there is 30 degrees. But it looks like maybe the angle here is roughly 45 degrees. And so option 4, or option 4 here would be slightly bigger than option 2. And of course, option 5 there, the torque is 0 because the force is parallel to the lever arm. In fact, it's anti-parallel, right? Because the lever arm is from here to here. Okay, let's go to the next question now. I'll be back shortly with the next question. And we're back with the next question here. What is the kinetic energy of a 120 centimeter thin uniform rod with a mass of 450 grams that is rotating about its center at 3.60 radians per second? We have a couple options, 5 options: 0.350 joules, 4.20 joules, 0.700 joules, 0.960 joules, 2.10 joules. Now, I've just gone ahead and given a relevant formula here for this one, and that is that the rotational inertia of a rod rotating about its center is 1/12 the mass of the rod times the length of the rod squared. Okay, but this is not the only formula that's relevant. Of course, a formula like this would be given to you on the test if you're required to use it. Can you guys think of any other formulas that might be useful here? Being asked to calculate kinetic energy. How would we calculate kinetic energy here?
One half the mass times the velocity squared.
Okay, so 1/2 mass times velocity squared doesn't exactly work. We'd have to adjust this formula slightly. If we adjust it slightly, then we can get a nice formula that applies for this question.
It's the same thing but angular, right? So it'd be
that's right.
the angular momentum, basically, instead of velocity, it'd be omega. It's the W looking one. Yeah. And then it would be the moment of inertia instead of the mass. Thank you.
Okay, so there you go. There's your formula for rotational kinetic energy. So 1/2 the rotational inertia times omega squared. All right, so if you're doing this at home, watching on YouTube, pause it now, and we'll be back in a flash with the answer and discussion. Okay, we're back, and after quite a long discussion, we have settled on this answer here, answer A. What you need to do is you need to convert 120 centimeters to meters. You need to convert 450 grams to kilograms. And once you do that, you can calculate the moment of inertia of the rod about its center. So 1/12 0.450 kilograms times 1.20 meters squared. I'll let you fill in the answer there on that one if you're watching at home. And once you have that number, then you want to take that number and plug it in to this expression here. So 1/2, whatever that number is, times 3.60 radians per second. No conversion necessary there. If it was given to you as RPM, revolutions per minute, you might have to convert that as well. And ultimately what we end up with for the answer is 0.350 joules. Answer A is the correct answer. Congratulations to those of you who got that one correct. Okay, so I'm going to go ahead and pause the recording, and I'm going to let the group decide if they want to do more questions or if we'll end it there. And if we decide to end it, we'll just stop here.